Okay, this is part 2 of day 1 of 6.3 and dealing with parametric equations. As I stated in my last video, before we can go on, I need to prove one of many trig identities for you. It is probably one of, if not the most important trig identity. So I've already written it out for you to save some time. I have placed this in the content library so you can thoroughly look through it. But if you look at the reference triangle I have drawn, we know that x squared plus y squared equals r squared. We also know from when we did our trig with our unit circle that the x coordinate of any circle is r cosine theta, and the y coordinate on any given circle is r sine theta. So here's my proof. This is my proof of this identity. I would like for you to pause the video and take time and look through it. So I'm referencing colored equations just to help us follow along. You could see that x squared equals r squared cosine squared theta and y squared equals r squared sine squared theta. I end up adding those equations together. I do some factoring, and in the end, I prove that cosine squared theta plus sine squared theta must equal 1. You need to know this identity and the manipulations of it. I'm hoping we can circle back at some point in time and go through many of the trig identities. I'm going to go back to the note sheet that was sent to your OneNote. And we left off here in the first video, and now we will continue on. So a parametric equation is an equation that defines both elements x and y in terms of a third element, the parameter t. T often represents time or an angle. So go ahead and read this paragraph by pausing the video. So we learned that there are two forms that we're dealing with. We're dealing with function form and parametric form. And so today we're going to go ahead and work through some parametric equations and then rewrite them in function form. So I would like to revisit the boat problem. And I have my x component of boat 1, and I have my y component of boat 1. Okay, so to eliminate the parameter, we would like to eliminate the parameter t to get it back to function notation where we just have a y equaling f of x. So if I look at this example, the easiest equation to begin with to start eliminating the parameters y equals 2x. I'm sorry, y equals 2t. So I'm going to say t equals y over 2. Now I'm going to take this t and plug it into the t for the x. Now that is not the only way I could have done this. I could have used my horizontal component x and solved that for t. This was just the first thought that came to my mind. So I'm going to go ahead and I'm going to say x equals -8 plus 6. I'm going to go ahead and take that y over 2 and I'm going to simplify. I have simplified my equation. You can see that in purple. Now I want to get y in terms of x. So just some basic algebra here. I'm sorry, that should be an 8. And so I get y equals 1/3 x plus 8/3. So I have a line segment let me back up. This is a line, but I can make it a segment by putting a limitation on the parameter. So if I put this limitation on the parameter to make this a line segment, let's say I do something like this. T has to be greater than or equal to 0 or less than or equal to 4. I'd like for you to figure out where the line would begin and where the line would end. I'd like the points. Pause the video and find those. So I've given you a visual giving that restriction on time. And you could see that I've graphed it here, and I put the restriction on time. And so hopefully you understand that if I plug 0 in for time, my x component is -8, my y is 0. And if I plug in 4, I would get 16, 8. I can see that by looking at my table from what I've plotted. I have that -8. And if I scroll down, I'd see that last point. Let me just go ahead and do it this way. I'll start my table at 15, and then we'll quickly see that last component. I'm sorry. I will change my table back to just going to 4. Just want to emphasize those two numbers. So if I look at when time is 4, I have that 16 and 8. Okay, my last example from the day. Now this is by far, in my opinion, the hardest one that we're doing today. And that's eliminating the parameters when we're dealing with trig functions. So I'm going to go ahead and take the parametric equations from the Ferris wheel. Then I've got to think about what to do. I want to recall that I now know this trig sine squared t plus sine squared t equals 1. So I want to get that. So the first thing I'm going to do is isolate those two things. So I'm going to just leave the horizontal or the x component alone, and the vertical component I am going to go ahead and get that isolated. I need cosine squared and I need sine squared. So I need to square both sides of these equations. Go ahead and rewrite this here. Now, I don't need to simplify that binomial that's squared. I don't care about that. In fact, it would make my work a little bit more challenging. All right? And so our next step is to add the two equations together. And I can see the equation of a circle forming. And so I'm going to go ahead and factor out 9. Because of our trig identity, we know that this equals 1. And when we put this, I will not call that a function form because it's not a function, okay, but more of a scalar equation form. I know I have a circle with a center at 0, 4, and a radius of 3. If we go back to that parametric equation we graphed in the first video, we can confirm that that is what we have. We have a circle with a center at 0, 0. I'm sorry, at 0, 4. And we have a radius of 3. So that concludes the lesson for 6.3 day 1. I will be live during the majority of your class time, and feel free to join in if you have questions. I hope you're all taking care of yourselves. Stay healthy.